Okay, thank you. Good morning, everyone. The topic I'd like to talk is dryness, urban dryness island effect from the view of satellite remote sensing. I'm from Beijing Municipal Climate Center and also called Beijing Ecology, Meteorology and Remote Sensing. The report contained four basic parts. The first background, as we know that the UHI has attracted more attention. Here is a histogram from a review paper that released. There are more studies about UHI in recent years. I guess there are more than hundreds of applications in these 2 years. For example, in this conference, I've heard about more than 10 reports about UHI, while UDI are rare, and however, it's an urban climate effect closely related to human settlements. The UDI has substantial impact on hydrology, ecology, and human settlement. For example, it could increase energy consumption and make urban vegetation water stressed. Thus, it will raise the fire risk and induce influenza virus dispersal threatening human health. Just as Professor Oak said, the UDI are the most complicated phenomenon in all urbanization's impact on local climate. Here, I try to summarize the reason for that. First, I think that it has a complex forming mechanism, like, for example, like the gasoline consumptions that will contribute to the UHI, while it will play a negative role on UDI. Second, I think there are more humidity quantities, like relative absolute vapor and so on. Third, the moisture has more status, like solid, liquid, density, and it keep shift from one to another quickly in short time. And fourth, there are more impacting factors like the urban morphology and the land surface temperature and anthropogenic moisture emissions and other things. So here, as I mentioned, the methodology and humidity quantities, like the vapor pressure, specific humidity, and water content and dew points. When you use different quantities, I think you will get different results, and even you get the opposite results. So here, we try to use two indicators. First is precipitable water vapor, and second, the near surface relative humidity. Both of them are involved from satellite data. Here is a study area in Beijing, and this is a map of in-situ stations. And there are more than 1,600 automatic weather stations, and in which there are 360 sites measuring the humidity. That means there will one site every 5 kilometers. And to the satellite remote sensing data, we employ the PWV for models and through in 3D, and also land surface temperature, land cover, and vegetation indices, and elevation. Here's the map of Beijing, and dark and green. The dark and the pink are the mountain area. To eliminate the terrain influence, we analyze UDI. We just use the green area and the plain area. And the green points are the observation stations. Inside the circle are central. The blue circle are the central urban. So the study are divided into three parts. The first is from the total column PWV, and the second is we want to see how the situation about the bound layers moisture island, and third we want to see whether it's consistent with the near surface. So here's a map of the annual accumulated local, the total column PWV. We can find that it shows there are some years, in recent years, the amount of PWV is relatively higher than ever before. And after calculating the UDII, that is defined as the value of every pixel minus the average value of the suburb. We got the map of UDII, and visually we can find the UDI effect exists, especially in year 2008 and 2014, 2018. To quantify the changing characteristic, we here define them both is the time series of annual UDII, both in the central air and the core air, and they both showed a decreasing but less significant trend. And in the year 2008, it's the abrupt change and the lowest, and the strongest or the magnitude exceed about 15 millimeter. And add to the seasonal variation, and summer contribute the most. And besides, we want to see to validate whether it's consistent with the near surface level. So here is the result based on the stations. We found that something different up to the relative humidity-based UDI, and the strongest in the autumn, but the other two, the vapor pressure and the absolute humidity is in the summer. That implied us when we analyze UDI, we should use more indicators to reduce the uncertainties. And again, it's a proof of the complexity of the UDI. And here also we want to explore how urbanization affects the UDI. So here all the three indicators show a tendency trend, but the built-up areas show an upward trend. And add to the scatter diagram, the built-up areas explain the changing of the relative humidity-based UDI, and at the explanation over 50%, and up to the vapor pressure, it explained more than 40%. However, only the the absolute humidity only has the power of explanation and of about 20% is has a weak correlation with the good up. But the second part, we show a vertical map of the difference of absolute humidity in every pressure air. We found that something different, that in the urban air there is about 100 and 155 gram per cubic meter water. But in the suburban, it's about below about 100 gram per cubic meter deficit. So in the upper layer, there is the water island. So in the third part, we want to see how is the situation in the near surface air. But, first, we built a model to estimate the NRH here by machine learning. Here, 5 algorithms were employed to get the best one. Like multi-layer perception, random forest, and decision trees, adaptive boosting, and gradient. Here's the results. In the model, the random forest performed the best, and he got the RMC with about 5%, and to the validation, it's about 10%. So, and we want to the variables, the TPW contributed the most, over 50%, and only 3D models are approximately equivalent. And we also analyzed the error distribution. We found that the stations with the error below 10% account for more than 80%. And add to the seasonal variation, they are almost close to each other. So here's the map. Here's the map of average NRH estimation in year 2021. And the left, both of the Phoenix 3D and models, I think, capture the UDI effect, but there is some place difference. Here in the circle area, I think they are the mountain branch. And also we want to see how it changed from the near surface, from suburban to urban, and this is the cross intersection profile. You can see from forest there is, with high value, and then to dense building areas with the lower value from the, and then farm and water in the suburban value are with low value. Also, we want to see how is the situation in from the whole area in Beijing, and this is a map of UDII in 2021. We can see both models and Phoenix depict UDI effects. Image strong UDI in central urban, while weak UDI in surroundings and no UDI in suburbs. And also, besides, we employ the UDPI, that is weighted air proportion sum of different level UDI, to see whether it's consistent with the PW is the UDI, and so, but it shows the strongest is in three, that is different with the previous study. Further, we analyze the changing characteristic in years, and here we found that from 2002 and 2021, most central air zones are in stronger UDI level. From in the first years, the UDI fluctuated, and at last, okay. So the conclusion is significant that UDI effects under clear sky in Beijing, and we should pay more attention to when we analyze UDI. That's all. Okay, that's all. Thank you.